this course Newtonian mechanics with examples, let us continue our study of statics, that is the mechanical equilibrium for with different examples. In the last few lectures we reviewed the tension force and we sort of told about the different properties of the tension force when it is uniform, when it is along the line of tangent and so on. And then we considered an example of a interesting and very common example from everyday life, which is about the ropes, hanging ropes or hanging cables or suspension cables. Today the plan is to take another very interesting and very common example which has lots of practical engineering application as well. So, today we are talking about truss or the framework. So, here is the plan for how to go about it. So, first we will take a few examples and then we define the question that we are going to analyze. Then we will use our systematic method of analysis and take different worked out example to sort of tell you how to solve this kind of problems. Then we will consider a very important question, which is that under what condition we can determine these tension forces uniquely, and we will see that this problem is really interesting because this is usually when we talk about truss, the things that comes to our mind are from mechanical engineering problems or civil engineering problems, but we shall take a very different situation and example, and we will show that this kind of analysis is very generally applicable to other kinds of problems which you may not usually think in from your engineering curriculum. And I particularly like this problem because it sort of gives you a very interesting way to see the relation between the basic physics and basic physical principles and the engineering point of view or the application point of view. So, let us start. So, here I show you 4 different pictures. So, one picture is a part of a bridge, the another couple of pictures, this one and this one, are about roofs, and this is a picture of a crane which is supporting a load. Now, what is common about these pictures? So, what is common about these pictures, and in all these cases there is some sort of an external load such as this car or whatever tiles you are going to put on this roof or this roof and this roof here, this load here. And to support this load, the engineers have designed a framework of beams joined together. So, such as what is shown in this picture here, and this the wooden beams that are connected. So, these are the and this crane is made up of these connected beams. So, these are kind of the important engineering structure, and the goal is to keep the whole thing in equilibrium such that this bridge does not collapse or this roof does not collapse, or the crane is able to lift this weight in a safe way. Now, so let us continue more. Now, if you are going to be looking at this problem from a mechanical or civil engineering point of view, maybe you are going to be interested in designing this kind of framework. Now, I should clarify here that in this course our goal we are going to study this problem from physics point of view. So, our goal is not to teach you how to design different kinds of frameworks, but to sort of help you see how you are going to apply basic physical principles, so the simple conditions of force balance and torque balance, to sort of that will enable you to design arbitrary types of structure. So, let us define more precisely what is truss. Truss is a framework. Framework means like these beams which are connected. So, it is composed of members joined at their ends to form a rigid structure. So, this word rigid is important, and this is called as truss. And examples are like as you shown before, the bridges and roof supports, etc. Now, if I say in a plain English, then you can simply from physics point of view, you can simply think of the truss as some sticks such as matchsticks joined at the ends. Like if you take some matchsticks and join them by glue at the ends, and then you can build this kind of frames, and that is our toy example of a truss. Now, note that there are two types of frameworks possible. One in which these sticks joined and these frames are forming a planar structure, which means all the sticks or beams they are in the same plane. So, this is a plane or two dimensional truss. The other possibility of course is that so let us say for example, using 4 sticks in plane you can make a like a quadrilateral, but in 3 dimension you can make a pyramid. So, this is an example. So, 1, 2, 3, 4, 5, 6, okay, there are 6 sticks here. So, this is an example of a 3 dimensional framework, or which is also called a space truss. Now, we are going to, for simplicity, we are going to take examples with 2 dimensional truss. It is easier to draw and analyze, and again, but the method of solution will remain more or less same if you go to 3 dimension. It is just the calculation becomes slightly more complicated. So, let us now define the question. So, what we are going interested in is that in a given we are considered this situation where there is some external load such as this car on the bridge, and there is a structure such as this framework of beams which makes this bridge. So, which is supporting this load, and this important point of the structure is that these are not a continuous structure, it is made up of sticks, and these sticks are joined connected at some joints. So, there are some supports from the joint. So, these are the 3 pieces. Now, we want to know that, so we want to analyze how this external load can be supported by this framework. So, such as the questions we can be interested in is that, so to support this load there will be some internal force, or which we call the tension force, which will appear in the beam. So, how much is the tension force in these beams, and how much is the contact force at the joints? So, these are the 2 crucial questions whose answer will determine the stability of such structures or rigidity of such structures. Now, of course, we need a few assumptions to simplify our problem, because in general it will be clear in a moment, in general it is a difficult problem. Why? What makes this problem difficult? So, these beams are actually a massive structure, like if they are made of steels or irons, they are massive heavy structures, but we are going to assume that these beams are massless. Now, we have reviewed this assumption in one of the previous lectures. So, it basically means that the external loads are quite high, so that the weight of the individual beams can be neglected compared to the load they support. So, this is a very simple assumptions, because we saw that it sort of immediately it follows that the tension force along the beam is uniform throughout. So, we do not have to consider the variation of the tension force along a beam. So, in that case you can sort of think of these beams as kind of a transmitter of force between 2 joints. The other assumption required to a very important assumption is that we are going to assume that their lengths are also fixed. So, the distance between 2 joints is always the same, no matter what the external load is. So, there is no extension, no contraction, no any kind of deformation or crack or fracture or some sort of a torsion or bending or twist, swing in air, etc. So, all these kinds of motions are possible for real such structures, and they are important. Like if you really want to build a such structure, you want to consider all these important effects, but for our analysis we are going to ignore those effects to make our life simple. So, this is actually a very idealistic situation, but this will sort of tell you that our focus is on the learning free body diagram and applying basic conditions of force and torque balance. So, we are going to ignore all these things. So, those of you who are kind of will be actually thinking of doing design of bridges, etc., they will consider all these things in your respective engineering discipline in later years. So, if you ignore all those effects, then the only internal force that the beam can support is the tension, which is a force that is acting along the length of the beam in at a direction which is tangent, and we are going to assume that there is no bending of such beams. These beams are basically straight line. So, there is no curvature of the beams, unlike the previous problem that we discussed of suspended cable or hanging rope, where the rope was perfectly flexible, so that it could but in this case we are going to assume that these beams are perfectly rigid, inflexible. So, the tension force is always along the direction of the beam, and because we ignore all those other kinds of internal force, different kinds of deformation of the beams. So, it immediately, and the beam is massless. So, it immediately follows that tension force is uniform throughout the beam. Now, in this case our problem is what is called a simple truss. So, that each beam element or each element beam, you can sort of think of it as, so this is connected at two ends by some support, and the only interaction is happening sort of as if happening only at the support. And so, this beam is so if you consider this one beam as your system, then the surrounding is and the support. So, this is, if I consider this as my system, and then the support is in the surrounding, then the beam is interacting with the support at the end. So, for the if the whole beam is in equilibrium, is in a static condition, it is motionless, it is not moving, then it immediately follows that the forces by the surrounding, that is by the support end of the joint of the beam on the beam, must be equal and opposite, so that the net force is 0. Now, there are two possibilities: either the these contact forces between the beam and the support is directed towards the support, away from the beam. In that case, it is by convention it is called a tension, or the contact forces. So, these are the contact forces, contact interaction between the beam, that is our system, and support, that is the surrounding. The other possibility is that the direction can be in the opposite, so that the beam is the support is putting a force which is into the beam. In that case, by convention it is called compression. So, this is about the direction. There are just two possible direction along a straight line, and the for the force balance, these two forces at the end must be equal and opposite. And the other thing is that so just to say it on from the other point of view. So, in return, because these contact forces are in like real interaction. So, by Newton's third law, if the forces are giving contact supports are exerting force on the beam, in return by Newton's third law, beams are also exerting forces on the supports or the joints. So, for example, if I look at this diagram, so let us say there are these two beams which are joined at this point at the support, common support, like which is also called a node. So, then the AB is the force by the node on this particular beam, and sorry this force is the force on the beam by this joint. So, by Newton's third law, this is the force which is the reaction force. So, this force is by the beam. This is a beam, and this force is on the beam. This is on the joint, and this is by the joint. So, they are action reaction pair, and we are going to also assume a crucial assumption that all the forces, that is, if there are more than two or more than two beams are connected at a common joint, then the line of action of all the force are passing through the same point. So, this is a simplifying assumption. I mean, the point is that in general this joint covers some particular area, but we are going to replace it by a point. So, we are going to assume that the line of action of all the tension or compression forces are passing concurrent. Now, the second important point that we need to keep in mind is that the contact forces and the torques between the beam and the support, it depends on the type of the joint. So, there are several different types of joint possible. For example, this type of joint that is shown in this picture is called a pin joint, because this is a pivot point, it is a common point, and this beam is sort of, so this red part is the fixed part of the support, and this blue is the beam, and this is kind of hinged at one point as if of the support. So, this is called a pin joint, and again there can be two kinds of possibilities. So, for example, this joint can be kind of welded together in a way so that this beam cannot rotate. So, let us consider the case where the beam can rotate. So, it is free to turn. So, in this case there is the beam, you can see that it cannot support any torque, because if you apply even a small amount of torque on the beam on the beam, and then the beam will rotate. So, this type of joint, pin joint, will not support any torque, but there will be some force, and this force in general is can be in any direction. So, this force is a plane. So, this support is and the beam together they form a plane, let us say the plane of the screen, and in general there will be two components, so there will be a force, and in general this force is unknown. The other possibility is that the beam is kind of welded in such a way that the beam cannot rotate. In that case, the difference is that in that case not only there is a contact force, but also there could be a contact torque, which is denoted by this quantity m, the moment of the force m. Now, there could be another type of support is a fixed support, such as this rod or beam which is inserted in some wall, as if it can be also welded. In that case again there could be in general there could be a force which is along the axis, and now and there could be a torque. So, this joint can also withstand a torque applied on it, because it is fixed, and it can withstand a contact force. Now, this in general this contact force, like in this example and in this example, can be in I mean this is this will be in the plane of this support, but it need not be along the axis. It is only when we ignore any force, internal force which is perpendicular to this axis, such as shear force which arises because of the deformation of the beam, only then we say we can assume that this force will be perfectly and along the axis. Similarly, in this previous, in the pin joint case, in general the direction of the force can be different from the axis of the beam. But if we make those assumptions that such that we ignore all other kinds of internal forces like elastic forces etc., then this perpendicular component cannot exist, and there is a simpler version where we can assume that our force will be along the beam. And then there is another let me mention another type of support which is called the roller support. In this particular case, so there is a the support point, the pivot point is put on a roller, and we assume that there is no friction between the roller and the surface on which it rolls, and it can move in the horizontal direction. So this kind of support, the point is that there can be only the force in the normal direction, because any force in the horizontal direction, in a direction in which the support can roll, it will make the support roll. So, it will no longer be in a condition of mechanical equilibrium. So, this is a roller support which can support only force normal to the supporting surface, ignoring friction. So, these are some of the common type of supports I mentioned, because it may be like you will encounter them in real life and various problems. So, given all these assumptions, let us now define the problem, understand the problem that we have, the nature of the problem or the type of the problem. So, what we have here is that this whole structure is at rest. That is the first thing. So, we can apply, so it is in a statics problem. So, we can apply the condition of force and torque balance. Now, there are two rules that you or two assumptions that not assumptions. So, this basically it follows from the Newton's laws of motion. If we apply the condition of force and torque balance, is that on any single beam, so no matter how complicated is your given structure or the framework, total force on any single beam is 0. That is the first thing. And the total force on any joint is also 0. So, for example, if we take some structure like this, so we have, it is made up of two parts. One is called a joint, or which is also we will call the node, some point, and then it is connected by beams or some straight lines, some sticks. So, total if the whole structure is at mechanical equilibrium, that means that the total force on any of the beam is 0, and as well as the total force on any of the node is also 0. So, these are the two rules that you should keep in mind. Now, let us also, in this kind of problem, you should be very clear about what is given and what is known and what is unknown. Usually in these problems, the external loads are known. So, you are going to design some structure which can operate within a given load, and then the structure responds by generating the tension force along the beam, and these internal tensions are kind of so these are essentially the contact forces at the joint, at the support, and these forces are unknown, because the nature of this force. So, this is a force, I emphasize this point again. So, this is a force contrasted to it something like a weight of the structure. So, if you know the mass of the beam, then or the mass of the whole structure, then the weight is always mass times the acceleration due to gravity. So, it is always known without doing any calculation, but the internal tension forces are unknown, and if we want to calculate those unknown forces, we have to apply these conditions of these force and torque balance and solve those equations to determine those unknown forces. So, we shall continue taking a concrete example and apply this framework in the next lecture. Thank you.